We sometimes want to remove the DC component from a signal without disturbing the rest of it. A couple of ways to go about this are adaptive cancellation and fixed DC notched filtering. Let's have a look at these two approaches. We have a Simulink model here making use of the DSP Speedster toolkit, and across the top third of this is what I want to understand to start with. We'll have a look at the first approach, which is going to be the cancellation. We have a strange waveform being generated. It's only 500 samples long. It's got a couple of distinct features inside of that one repetition of the signal. It'll get a chance to repeat 4 times because I'm going to run for 2,000 samples with a 20 kilosample per second sample rate, and so it's only going to be 0.1 seconds worth of simulation time. But as that happens, in this first blast of this, we will get a biasing of 0.4 volts added into this, and so this canceller needs to become aware of that and try to counteract it. It's a block right here which we'll be able to observe before and after. The yellow and the white trace will be before and after that special block, and what will be happening is that we will be finding the DC content in here and observing it on yet another single trace analyzer out here. Inside this block is an algorithm which has been put forward by Fred Harris of San Diego State University, an M file which he created using a first order gradient search algorithm to do this, and I'll show you now a Simulink interpretation of that by looking under the mask and seeing here the signal come through, pass out after having subtracted a current estimate of the DC content. So this is the business end of the algorithm. This is taking use of some fixed, we're using a 0.01 mu step size here. You notice there's not very much memory in this, so this action is going to be almost instantaneous, and furthermore it's a nonlinear process because you can see this floor operation here. So this is a nonlinear, time varying, signal dependent adaptive processor, so it's quite an effective little algorithm, as we'll see in just a moment. When we run it, the model, and have a look on this first trace, which is this one here, we see two things. Let me first get rid of the white one. This is the original signal in which it's experienced this 0.4 biasing blast here, and then that's dropped down to 0. However, I would have note here that even in this particular little piece of the waveform, there is locally a DC content that this is riding on inherently in the waveform. Now the algorithm is sensitive to that, as we see when we bring this in. I can get rid of the yellow one if you like. You can see this result. It's a bit scrappy. There's terrible damage done to the signal on the original surge here of the first period, and when that bias drops out, then there's a recovery phase 2 where it comes back in. So it's only out in here where we start seeing sort of steady state behavior. Notice the drop down of this droop right here, which is caused by having sensed that there is indeed a little short-term DC content which needs to be subtracted out. So this is a result which is, if I get rid of the yellow one, it's a little bit scraggly, and this is not too surprising because for this algorithm to exercise this, I've not given it very much of a fair chance. I'm only using 5 bits in the processing of that canceller, and this sort of ruggedness is also visible when we look at just the DC content. It's pretty instructive to have a look at that. I'll go out and grab it. This is just an estimate of the DC itself. You notice it feverishly builds up here to 0.4, and so far as it can with this heavy quantization of the processing, and then immediately starts charging back down because that bias has dropped out. But even out in here, it bravely attempts to take care of the small droop within the waveform itself. So that's what's going on in the canceller. Now if you think that's rugged, have a look at what's going to be happening down here. We're going to make use of a regular old initially relaxed DC notch filter out here, and we're going to compare its behavior with this yellow trace on this scope with the one that we've just seen for the canceller, which is going to be coming in here on the white trace again. Now, what makes this painful is that an ideal filter, all this block area right in here, is just to create the coefficients which are piped into this block right here, which actually does the operation. So we take the pristine coefficients coming out, the B and the A coming from a first order DC notch filter, which I've decided to have a 3 dB cutoff at 65 Hertz with this, where we have 10 kilohertz for the Nyquist frequency, so it's pretty narrow. And we're going to subject that to a comparable quantization. This is going to be the fractional representation of this bit word for these coefficients is going to be 2 to the 5th down here, so it's comparable to that. And we're going to see what comes out. Well, we're going to run the signal, which the system which we just did. So let's bring it up into visibility, and you can see what's going on. First, the top white trace is what we've already seen for the adaptive canceller, and an even more disastrous result has been encountered by this notch filtering operation. You notice it's driven way off down here, hitting a plateau and even another plateau, and it's damaged out here. It's a gigantic mess. It makes you wonder why it's such a gigantic mess when it's a regular old notch filter. Well, the answer is, let's examine before and after the quantization of the coefficients. The perfect ones will be in black here on this analyzer, and the quantized ones will be in red, so I need to call up that picture, and here it comes. Now you can see I've blown this up to only 1 kilohertz, so I'm going from DC to 1000 Hertz to zoom in on this very narrow notch area. And here it is down around, trying to roll off down to about 0.707 when we're at about 65 Hertz. This is the ideal thing, doing that quite well, thank you very much. What is far from a notch, however, is the red curve, which I remind you is the result of the quantization effect. And it is a giant mess, and therefore we've got clearly a worse situation in this case of small word length. So let me try a little bit nicer situation. If I come up to say by typing this into the command line and calling it n bits equal 7, so still not very wonderful as a budget. And now I compare the two algorithms, and I begin to see that the notch filter is acting a bit more reasonably. It's coming up here into the area being not so much worse than what we got with the adaptive canceller. Of course, the adaptive canceller itself is better than before, not near as rugged sort of quantizing of the results coming out. And if I go a little bit more, I think the boundary comes about n bits equal 8 or so. Run it again, have a look, and you see that they're coming in nicer and nicer. And I'll just go ahead and take the leap to go to 18 bits for kicks. And when I do and run it again, I now see that it's bang on top of each other. You can see they're right on top of each other. Scarcely any difference whatsoever between the notch filter result and the adaptive canceller. Still worth looking at what happens with the adaptive canceller. Much smoother now. Notice how its gyrations are quite sort of sensible things, that they're doing a big attempt to estimate the DC. And out here in these other 3 replications of that strange waveform, it's having to take care of a relatively small fish out here in terms of DC. So what's my conclusion? My conclusion that both of these operations can be made to be very similar. It seems that the DC cancellation algorithm has a lot to offer when you have severe quantization effects.